Okay, so now for the series towards StatPhys, we have today Emanuela Del Gado. So please, Emanuela, can you introduce yourself and tell us what are your interests, where you work, and so on?
Mhm. So I'm a physicist, a statistical physicist actually by training. I studied in Italy, and then after I moved to France, then to Switzerland, and I moved to the US 10 years ago. I work on soft materials, and I've always been interested in materials with complex microstructures, especially gels. And networks of various types, but also materials which have a lot of different components. And so processes like how do they flow, how do they accommodate deformation, how to respond to external stimuli. It's really about understanding the emerging properties of these many components that come together.
So, if I understood well, the field is called the rheology, which in some sense means how materials react to stress
Mhm.
when dynamical stress. So, can you explain us what is rheology about?
Rheology is really about, literally the term, how things flow. And in fact, of course, fluid flow, but also, in fact, also solid materials can flow, like rocks over millions of years. Uh, but basically, in particular, what is interesting is understanding the flow of materials with the complex microstructures. So, where the flow, in order to develop, in order to be maintained, require processes and sometimes different and complex processes that happen on multiple length scales and multiple time scales. So, you could think about something that reacts as a solid on a very short time, but there at long times it starts to creep. And where does this creeping behavior come from? It's something that we don't completely understand and requires, a lot of control in a number of applications. But also, it's the science that is so important. I think now, if you want to print materials, if you want to print parts, right, and you want to be able to design shapes and at the same time change the properties of the part to make it tougher, to make it stiffer, to make it more able to, for example, to resist changes in the environment, and so more durable, sometimes sustainable, and so on.
So, I remember having seen, say, people running over the mixture of corn syrup, no, corn starch, no, or also cream. I think there is a lot of rheology in how it prints.
So, all the materials that compose foods, for example, and this relationship between the texture of the materials and the way it flows or the way it's deformed when you eat it, when you swallow it, these are all the aspects that come in this type of studies. Personal care products, as you were mentioning, like creams and other toothpaste and so on, but also again materials that you want 3D print, what people call inks and bio inks for printing in the context of biomedical application now. If you want to print things that are much more complex, like organs or tumors, that would allow you to, to develop, for example, therapies that can be tested outside of the patient body. Um, one example that is very interesting to me right now, and I'm thinking about it a lot, is that cells in our body, they produce materials in which they are embedded in the tissue, what we call the extracellular matrix, and they are able to extrude the polymers that go in forming these complex structures, but which basically are a mess. But in fact, they are very well organized because the cells also control the way these matrices self-assemble, and therefore they control the way they can react to external stimuli. So that's how the cells can pull them apart or use them to sense what's outside of the extracellular matrix, and they are completely integrated in their clocks, in their biochemical pathways, but we don't know how this works. So
Mhm.
I've kind of gone through okay, how do I make things flow? How do I control things that flow into this idea that then I want to have materials that are completely integrated in the environment in which they live, and that's something that probably will come after.
You mentioned before gels. So please, can you illustrate what a gel is?
So a gel is a material that it's made of some solid component, which is usually in a structure of a disordered network, and it's embedded in a solvent. And so it's something that can be very soft, but it also has solid properties. So it has elasticity. It has a very frequency dependent, so rate dependent response. You were mentioning before running on the pool of cornstarch. A gel is something that will have a completely elastic response at very low rates, but in fact it can be very soft and nearly feels like it's flowing at very high rates. So kind of a bit the opposite of the cornstarch. But these gel materials, in many cases, and the ones that have been studied more a lot, are where this network is made of the solid component is made of polymer, which are polymerized to form this type of structures, and these huge macromolecules which can trap the solvent together, or it can expel the solvent, and it can be stretched enormously. But in fact, these gels form in all sorts of different contexts. Biopolymers typically organize into type of gel network. It's just that they have a very hierarchical organization. But also small particles, colloidal particles, can stick together to form gels, and this happens a lot in foods or in other type of materials. Paints or others, even in construction materials.
It seems quite a complex system, and you simulate it with a computer. So it is quite astonishing. How can you do that?
So you have to make choices and you have to be a bit courageous, right? And so I think that's why you need the physicist to do that, in the sense that you have to be able to choose which are the ingredients that you want to retain. Because sure, you could start from atoms. Maybe we are more familiar with atomistic type of simulations, but it's a bit, hopeless in when the material is this at this level of complexity, and it has this order of many different length scales. So what you want to do is to develop coarse grain models where you simplify the description of the materials, not starting from atoms, but for example, in the case of colloidal gels, you would start from particles and then identify or build a physical model for how the particle interacts. Sometimes you describe explicitly the solvent, but that's also very hard. And so sometimes you have they treat the solvent in an implicit way. So it's a context in which the simulations are very much embedded in the theoretical description that you try to give. And then depending on that theoretical description and the type of levels, there are certain things that you can do and certain things that you cannot do. Like I cannot, if I do that, I'm not going to be able to say anything or much about the atoms that compose the particles or the molecules that compose the particles. But I'm more interested in how the many particles then that are organized in this type of networks then determine, for example, the network topology and the interactions, right, lead to the network topologies. The network topology is optimized by what? By the fact that the material is trying to become rigid or needs to be rigid to sustain certain stresses. And so it's about studying these emerging properties.
So thanks, extremely interesting. I'm eager to hear you here in Florence. So to finish, what are you bringing to StatPhys?
So I am bringing the idea that one idea, but I think that now I can see this in many talks actually, and it's a as it often happens, there is an idea that develops in many different communities, but for some reason at the same time, this idea that things that are messy can be actually very well organized, and so statistical mechanics can be extremely useful to use tools from statistical mechanics, concepts from statistical mechanics, to try to rigorously understand this organization, and then I am very interested in particular, and I hope to be able to communicate some of that, on how this disorder is actually essential and plays a role then in the way these materials function. And I was mentioning, materials that exist independently from us, like the extracellular matrix or materials or the construction materials that we already use. Those are messy. We try to understand how to make them better, for example. But in the end, also, if we want to design new materials, having the capacity to understand how you can go from this multi-scale disorder and complexity to the function, to the recyclability, to the flow or to the failure, the ductile type of behavior, or the fractures and avalanches. This is something that I'm very excited to talk about.
Okay, thank you, Emanuela. Extremely interesting. So we wait you here in Florence. I hope that the weather will not be so hot as today, but Florence is like this. So
Yes.
see you here.
Bye bye. Thank you.